Welcome to This Explainer. Today, we're tackling a challenge that literally anyone who works with data knows all too well: rescuing a beautifully clean signal that is just buried under a mountain of chaotic data. If you've ever stared at real-world datasets, you know exactly what I'm talking about, right? You know the pattern is in there, but the static is just completely overwhelming. Well, instead of reaching for those heavy, computationally dense algorithms, today we're going to look at a solution that is surprisingly simple to implement, yet absolutely incredibly effective. Okay, let's dive into this. Imagine you're tracking something fundamental, say a slow, steady sine wave. It could be seasonal temperature changes, or maybe a long-term economic trend. But the data you're actually getting, it's a complete mess. It's jumping all over the place, full of short-term volatility. The underlying reality is perfectly smooth, but your sensor, or maybe the stock market, is just throwing a ton of static right on top of it. So how do we strip away all that chaos to find the truth underneath, without accidentally destroying the very signal we're trying to save? To picture this, let's look at a very specific scenario. Let's say we have our clean sine wave, but we throw in some Gaussian noise with an amplitude of 0.5. To put that into perspective, that means the noise is a full half of the signal's own amplitude. That is loud. If you try to fix this with a naive, single short moving average, which, let's be honest, is what most of us instinctively reach for, you're going to be pretty disappointed. A single pass just kind of smears the noise out. It leaves this visible, jagged jitter that makes any sort of accurate forecasting or analysis pretty much impossible. Which brings us to Section 1, the KZ filter explained. So, formalized back in 1986 for fields like climate analysis, the Kolmogorov-Zubenko, or KZ filter for short, is surprisingly elegant. It is quite literally just a centered moving average of a specific window size, let's call that M, applied K times in a row. And that's it. You just run a moving average, you take that result, and you run another moving average on it. You do that K times. It's kind of like purifying water. If you pass muddy water through a filter once, you get, well, slightly less muddy water. But if you take that same water and pass it through again, and again, and again, eventually it reaches absolute crystal clear purity. Let's move on to Section 2, why iteration beats size. Now, looking under the hood, it's a totally natural, highly skeptical question to ask, right? If I want a smoother line, why don't I just make my window size bigger? If a 10-day moving average doesn't kill the noise, why not just use a 50-day average and call it a day? I mean, why go through the hassle of doing a 10-day average 5 separate times? Well, here is the fatal flaw of standard smoothing techniques. A single moving average, no matter how massively wide you make that window, still leaves high-frequency ripples in your data. In the frequency domain, a single moving average has what we call side lobes, and these decay incredibly slowly, at a rate of 1 over f. What that means in plain English is that high-frequency noise just continues to heavily pollute your signal. It essentially leaks through the cracks of a single moving average, leaving your data wavy, distorted, and, well, just not good enough. Now, what's really interesting about this slide is the sheer mathematical magic of what happens when you iterate. Every single time you do a pass, you're convolving the data with a rectangular kernel. When you do that k times, you actually raise the frequency response to the kth power. Those annoying side lobes that were leaking noise, they get crushed exponentially. But the absolute best part is that, thanks to the central limit theorem, convolving that rectangular kernel multiple times rapidly approaches a perfect Gaussian curve. You get near Gaussian kernel quality literally just by repeating a basic moving average. How cool is that? All right, Section 3, 2 ways to code it. To ground all this theory in reality, the great news is that the KZ filter is trivially implementable anywhere. We're talking just a few lines of Python. Now, there are 2 primary ways you can actually build this into your pipeline. The first is what we'd call the textbook method, or the valid mode. This uses standard repeated convolutions with a uniform window. The second method is the pandas same length variant, and that one just uses the pandas rolling mean function with a minimum period set to 1. Both are incredibly useful, but they handle the edges of your data set very, very differently. So the crucial point is understanding the trade-offs between these 2 methods. The textbook valid mode has absolutely 0 edge bias because it only computes where there is fully supported data. But because of that, every single pass shortens the series by m-1 points. That results in a total data loss of k times m-1 points, so it's best for really strict, rigorous analysis where you can afford to lose the edges. On the flip side, the pandas variant uses shrinking windows at the edges. It's adaptive, so it's slightly biased, but it gives you a perfect 1-to-1 data alignment with 0 lost data points. This makes it a real game changer for feature engineering pipelines where perfectly matching data rows is absolutely critical. Let's wrap things up in Section 4, takeaways for your pipelines. When you actually fit the KZ filter into standard forecasting toolkits, these are the massive core advantages you're getting. First, you get a much sharper frequency cutoff than you ever would with a standard moving average. Second, it has this inherent robustness to missing data. Each averaging pass basically just ignores the gaps in your data, which, honestly, is a total lifesaver when you're dealing with real-world messy datasets. And third, it has a closed-form effective bandwidth. Mathematically, it cleanly passes periods that are longer than roughly m times the square root of k, while effortlessly attenuating the shorter ones. So how do you actually set this up for your own work? Well, here's an actionable how-to guide for picking those parameters. Step 1, choose your window size m. This should be based entirely on the shortest period you actively want to keep in your data. Step 2, choose your iteration count, k. Generally speaking, picking a k between 2 and 5 is the sweet spot. That's going to give you optimal side lobe suppression, crushing that high-frequency noise without over-smoothing things or just wasting your computer's processing power. And this brilliantly illustrates exactly why we care so much about this in modern forecasting. As the source material highlights, KZ Smooth series make excellent trend features and denoised inputs for downstream models. By separating out the long-term trend, the seasonal components, and the short-term noise so cleanly, the KZ filter is just perfect for building decomposition-based features. If you're feeding data into advanced machine learning models, giving them a perfectly denoised trend line as an input feature is going to dramatically improve their predictive power. We've seen the mathematical magic of the central limit theorem in action. We've seen just how easy it is to implement with a few lines of code, and we've seen how it perfectly preps your data for advanced modeling. So I'll leave you with this final, provocative thought as we wrap up this explainer. When you open your dataset tomorrow, will you stick to naive, single-pass smoothing that leaks noise, or will you upgrade your pipeline and iterate away the chaos? The choice is totally yours. Thanks so much for learning with me today.